So you can see we're on prompt 854, which is investigating what does the graph of cosecant of x look like. Now before we even start that, I want to first focus on the label for cosecant of x. CSC, that's what cosecant stands for. And that's the reciprocal of sine. And it's really important because when we see secant, it's very easy to get those two confused based off of the lettering. So CSC, cosecant of x, it's the reciprocal, so 1 over sine of x. Now we're going to go and do all parts here, parts A, B, and C, but first we're going to look at the table. And so when we did the intro, I kind of pulled up this and we showed you that you're really dealing with sine of x as reciprocal cosecant of x, and we looked at these around the first quadrant of the unit circle and the x and y axis in the positive direction. So we went through and did this. Now I'm going to fill in the rest of the table. And that way we can create this graph over here. So I'm going to go into the second quadrant. And so when I'm in the second quadrant, I'm thinking we're going to have 2 pi thirds, we're going to have 3 pi fourths, 5 pi sixths, and then the negative x axis would be a pi. So I'm going to fill those in. And really, if you remember this, they're going to have the same y values if you think about the unit circle. Because if you're in the first and second quadrant, you are at the same positives of the unit circle. So I'm actually going to look at pi thirds, which is radical 3 over 2. 3 pi fourths is going to follow pi fourths, radical 2 over 2. 5 pi sixths will follow pi sixths, 1/2. And then pi has a y value of 0. So I've already found all these reciprocals, so I don't need to do all this rationalizing again. I just go ahead and look at what it was and fill them in. So we have that one. Now that's the second quadrant. Let's go into the third quadrant. So be careful though, because in the third quadrant, we're now dealing with the negative y values. So I'm going to have the same blue numbers, but I'm just going to have some negatives with it. So let's see, 7 pi sixths, probably 5 pi fourths, and probably 4 pi thirds. And then let's do the negative y axes. So 3 pi halves. So 6, if it was positive, it was 1/2. So I'm in the negative, so that's going to be negative 1/2. Fourths was radical 2 over 2. So it's going to be negative radical over 2 over 2, and so on. Now I'm going to take the reciprocal of those. Now you have to be careful. When you take the reciprocal, the negative sign doesn't magically go away. The reciprocal of negative 1/2 is negative 2. The reciprocal of negative 1 is negative 1. So we just flipped them, and we did end up having to rationalize, but we didn't have to show it because we've already done that before. So now we're in the fourth quadrant. So if I'm in the fourth quadrant, I have positive x's and negative y's. So it's going to be along the same lines. And so here we have our radian angle measures. We're going to have still negative y values because we're in the bottom half of the unit circle. And I'm going to have those same type of numbers reflected around. So this is our table. This is kind of what we're dealing with. We are going to plot, and we're going to do this together. I'm going to plot the blue. We all know what the graph of sine of x looks like at this point. So let's just graph sine of x. And then we're going to take the reciprocal. We're going to plot the purple points and see what that looks like and how the relationship works between the graph of sine of x and the graph of cosecant of x. Now, by the magic of technology, there's the graph of sine of x. We have all the points plotted, and that way we can see what's going on. I didn't plot the radical 3 over 2 because that's just difficult. But I did plot the other ones. And what we're going to do is we're going to take the reciprocal. Now you can see there's a couple of purple points already there. And those are there because the reciprocal of 1 is 1. The reciprocal of 1 is 1, and so on. So I mean, I just went through and kept those as purple because those are going to follow the cosecant of x. Now we're looking at this. We are going to go, look at the points and kind of analyze what's happening. So let's just deal with the positives. Because I didn't look at all with the negative radians. So let's just deal with the positive radians. And let's look at some of the points. So if I were to plot these, let's see, pi 6 was 1/2. So I'm going to flip that, and that should give me 2. And then I should have pi halves, which was 1, we already said. And so if I plot those points, I'm going to get this, which is really interesting. Because it kind of looks like the other one, except for it's curved upwards. But look at that. It does look like it's flipped a little bit about that maximum, but I'm wrong with my graph right now. Because really, if you think about it, I'm only looking at 3 of the points, but I have a full table over to that side that I need to analyze. And I've yet to even look at some crucial restrictions. So don't get tempted to just go, oh, flip it over and just graph it like that. It's not going to work that way. We have to think about all the points. And if you think about it, I have ignored 2 very crucial points. And so we are going to just kind of leave it like that. Now I'm going to show you what the shape looks like. And so the shape looks like that. And you may go, well, that was the same thing I drew. And it's not, though, because what I drew was, it just looked like a parabola that went through it. And it's not a parabola. A parabola would go to the right and left forever. This is doing something interesting that we will look at a little bit later on. And I can follow the same idea with the pi to 2 pi interval. I can take those points from the table, I can graph them, I can plot them, and again, don't be tempted to go parabola opening downwards. Not going to work that way. And so I'm going to just do the curve. That is what the curve looks like. Again, you may think that's a parabola. It's not. A parabola would be going forever to the left. It would be going forever to the right as well. Ours doesn't seem to be doing that. And so then I'll just go ahead and reflect that over on the negative side over here. And you can see this purple is mostly the graph of a cosecant function. It is the original sine function flipped, except we did not address one of the numbers. Now I didn't address the radical 3 over 2 or radical 2 over 2 because those are hard to plot, but there is an easy number in that table that we could plot. 0. All those zeros on that x-axis, those are crucial. Because when I take the reciprocal of 0, I get undefined. And what does undefined look like graphically? It looks like a vertical asymptote. And so that's what I'm going to do, is anywhere my graph hit the x-axis, I'm going to put a vertical asymptote there. Now you can see why I was saying it's not parabolic in shape. It does approach asymptotes. So they do curve, like, oh, it looks parabolic, but they're not extending left and right forever. There's a boundary that contains those shapes. So we have to plot those asymptotes. And so the main idea is if you can graph a sine function, you should be able to graph a cosecant function. But some of the things we have to keep in mind is kind of backwards of what we did. The first thing you should plot are the asymptotes. Just think about when we do rational functions, even when we graphed our exponential functions, or we graphed logarithmic graphs, we graphed the asymptotes first because it gave us a restriction, it gave us a shape. So when I graph my sine of x, I'm going to first look at wherever it crosses the x-axis, and I'm going to flip it. Now in this case, it's the x-axis. In the grand scheme, it's not always going to be the x-axis. It's going to be the midline. And so we have to keep that in mind as, okay, right now it's the x-axis, but if I were to move this graph and do vertical translations up and down, it's going to be the midline that we're looking at. So that's the first thing. Look at where it crosses, I would say, an x-axis. I'll correct it to midline for the future. Then draw the asymptotes. That's going to give you the restriction. Then how do I get the bumps to flip? Well, just take a look at your max, or take a look at the min, and just flip them down towards the asymptotes. I'm not going to have you find these points. We're just going to use the maxes and the mins, and we're going to reflect over that way, but you have to make sure they are contained with the asymptotes. Now this is a very beginning stage of graphing cosecant functions. Now let's answer the rest of the questions. So part C says describe the graph. What are the domain and range of it? What are the intercepts of cosecant of x? Are there any asymptotes? If so, write the equations. We're not going to go into that much detail with writing the equations of every single asymptote. It follows a pattern. But I'm going to kind of show you there are some domain and range things that we do need to be aware of. It's the reciprocal of the domain and range of our sine graph. And so original sine graph goes from negative infinity to infinity. Look at the blue curve. It goes all the way left to right forever. However, what is the domain for our cosecant? It looks like it goes from negative infinity to infinity. Very similar, except for we have those red dashed lines there. Those are your asymptotes. So I have to kind of keep that in mind. Is my domain is everything except for pi times n, where n is an integer. So again, not an equation that you're going to have to be able to write down, but you need to be aware that there are going to be vertical asymptotes. That's the idea that the domain for cosecant of x is not negative infinity to infinity, because anywhere across the midline is going to become a vertical asymptote. Now the range for sine was negative 1 to 1. What's the range for cosecant? Well, look at the purple. It doesn't go below 1. I mean, it goes from 1 to infinity, at least for this positive. If I go down here, it goes from negative 1 to negative infinity. So that's pretty interesting, but in the middle, it doesn't do anything. So our range is going to be from negative infinity to negative 1. It does include negative 1, so it's going to be a bracket. And then a gap, and it's going to go from 1 to infinity. So range, you have to realize it's not going to contain the range of our sine graph because it's flipped. Now part D says describe the relationship between sine of x and cosecant of x. And this is kind of what I've been saying in words throughout this video, and I'm just going to give you time to kind of read through it. Is every single, it says x-intercept, and notice I put in red there, it says midline. Every single time your sine graph crosses the midline, it's going to create a vertical asymptote for cosecant of x. And that's because the reciprocal of 0 is 1 over 0, which is undefined. And then you have this concavity, just think opening up and opening down. It's flipped about those maximum or minimum points. And that's because the reciprocal of 1 is 1, the reciprocal of negative 1 is negative 1. So really this is kind of even the order that you're going to graph it. You're going to first find where the graph goes in the midline, draw all the asymptotes, and then take the max and mins of your sine graph and flip them. And that's going to give you the graph of cosecant of x. So hopefully this kind of provided a good introduction to what the cosecant of x graph looks like and why it looks like the way it does. But this is the end of prompt 854.